You probably reach for a vector database long before you actually need one, and I measured the moment you do. I loaded the very same embeddings into a vector database and into 10 lines of NumPy, then checked which one actually found the right answers, and one of them quietly dropped half of them. Before the numbers, the usual promise. Every result here is reproducible. By the way, if you want to run these benchmarks yourself, I've linked the raw JSON data and the React code I'm using down in the description for free. Here's the setup, and the one trick that keeps the test honest. I generated a few 100,000 fake embeddings, 384 dimensions each, clustered into realistic groups rather than spread at random. Then I ran the same 200 queries through each option and asked for the 10 nearest neighbors. To grade them, I computed the true answer the slow, boring way, brute force cosine similarity in NumPy, every query against every vector, which is exact by definition. That gives me recall at 10. Of the 10 genuinely closest results, how many did each engine actually return? It's the one number vendors actually never print, and it's the whole game. The grading is almost insultingly simple. Here it is. For each query, take the engine's top 10, intersect it with the true top 10, and count the overlap. Sum that across every query, divide by the total possible, and you have recall. There's no room for interpretation. Either the right vector came back or it didn't. The full corpus generator and every laner in the repo seeded, so you'll get the same numbers I did. Now let's point it at a real vector database. Start with the number that brochures never print. Did it actually find the right neighbors? At 10,000 vectors, Chroma, running its default settings, returned about 97% of the true matches. Very respectable. At 50,000, that fell to 77%, and at 200,000 vectors, it landed at just under 50%. NumPy, the brute force baseline, sat at a flat 100% the entire time, because exact search cannot be wrong. So as the data grew 20-fold, the vector database quietly slid from mostly right to coin flip. At the largest size I tested, the vector database missed about half of them. Sit with that, because it's the failure mode nobody warns you about. Your search doesn't error. It doesn't slow down. It returns 10 confident results that look pretty reasonable, and 5 of the 10 things you actually wanted are simply absent, with no flag, no warning, nothing. If that index is feeding a retrieval augmented chatbot, half the relevant context never reaches the model, and you would never know from the output. It just gets vaguer and you blame the prompt. Now the reason people put up with that, speed. This is where the vector database earns its reputation. At 200,000 vectors, Chroma answered in about 9/10 of a millisecond, while brute force NumPy roughly took 23. So the index is around 25 times faster. That sounds decisive until you read the two charts together. You're trading exact complete results for an approximate half-empty answer, and the price is shaving about 22 milliseconds off a query most users will never perceive. 23 milliseconds for perfect recall on a laptop is not a bar most applications need to beat. Here's the punchline, the hype skips. For a lot of you, plain NumPy is enough. If your corpus is under a few 100,000 vectors, which covers an enormous share of real projects, internal search, a docs bot, a side project, brute force gives you perfect recall in tens of milliseconds with no index to build, no recall to tune, no service to run, and no monthly bill. The vector database isn't a default you reach for on one day. It's a tool you graduate into when brute force genuinely stops fitting in memory or stops being fast enough, and not 1 second before. So is the vector database broken? No, and this is the caveat that matters, because I want this to survive scrutiny. Those recall numbers are Chroma's out-of-box defaults on a deliberately hard clustered dataset chosen to expose exactly this. Approximate search has knobs, how many neighbors it considers, how carefully it builds the graph, and turning them up recovers most of that lost recall. But it isn't free. Better recall costs you query speed, more memory, and slower index builds. That's the real trade nobody puts on the pricing page. The lesson isn't vector databases are bad. It's measure your own recall, because the defaults can quietly betray you, and tuning is a cost. And when your data is really big, here's what the managed options cost. Once you're past brute force, the bill is set by one thing. An approximate index has to live in memory to be fast. So you rent RAM by the gigabyte, modeled from published prices. Hosting a pgvector index on managed compute runs at about $75 a month at 1 million vectors, about 425 at 10 million, and roughly 3,700 a month at 100 million. Pinecone's serverless tier is actually free at 1 million vectors, but that index slips under their 2 gigabyte free allowance. But the moment you outgrow it, you're on their paid floor and usage on top. The pattern under every one of those bills is the same. You are paying to keep the index in memory. That's why cost scales with the number of vectors times their dimensions. It's a RAM tax, not a magic search tax. 100 million embeddings at these dimensions is a couple of hundred gigabytes of memory that has to stay resident, and whether you rent that from Superbase, from Pinecone, or set it up by yourself, the laws of memory don't change. Which, if you saw the last episode, should sound familiar. Renting versus owning the hardware is the very same decision wearing a different hat. Here's the verdict, measured rather than guessed. Under a few 100,000 vectors, start with brute force or a carefully tuned embedded library. It's exact, it's fast enough, and it basically is free. Reach for a managed vector database when your index genuinely outgrows memory, or when you would rather pay someone than run the service yourself. Just go in knowing it's a RAM bill, and always measure your recall, because the defaults dropped half of mine. The data and the code for all of this are linked below. If measuring the hype against real numbers is your kind of thing, subscribe. This has been the Validation Set. I'll see you in the next one.